Okay, hi everyone. So I guess if you stayed, because the title of the previous presentation, which was a very nice introduction for this talk, well, do you wanna have a post-quantum signature? And if you've stayed, and the title could be changed to no, you have it. So we are ZKNOX. I will briefly talk about ourselves. So we have been funded. We are three. So Nicolas Bacca is the father of the Nano, Ledger co-founder. Myself, I've been at Ledger. 2 years ago, I shipped the fastest solidity verifier for P256 because for the previous talks, there was some question about the efficiency and the gas cost. So I think I can do a good thing because I shipped this 2 years ago. It was like a factor 12 that we gained. This is kind of the same we had here. So I think we have reached the limit. And Simon is one of the authors of Bandersnatch. So what we do, basically, we ship things on the whole chain. So from hardware implementation to on-chain smart contracts, that's what we will talk about today, and also provide academic research. Okay, so what is quantum apocalypse? If you didn't get a sleep during the last talk, you know what it is. So globally, the test that Vitalik said, you don't have to be afraid. You should. I think if there is a quantum apocalypse tomorrow, you should find a bunker, because I used to work in the French defense, and we will have other problems than Ethereum if there is a quantum computer tomorrow. So when will it come? Good question, and it depends for who you are. So basically, if you are an SEC researcher, or if your products use Grot 16, it's basically never. If you're a PQC researcher, it's tomorrow. And if you're an average user, you're somewhere in the middle, but be aware that hold your bag, basically, is like a polymarket bet on the quantum rising. Okay, so we have talked about this quantum apocalypse. Just to separate things, authentication must be solved later, soon, because we want to have everything on shelf to be able to push on the emergency button for this hard fork we were talking about. But confidentiality should be solved now. If you use a private payment system such as Reno, you are using ECC. The encryption keys, the viewing keys are using ECDH. So this means that someone recording all the transaction will be able to decrypt later and get rid of your anonymity. So there is this separation of the urgency between authentication and confidentiality. So as we have talked before, so Ethereum components at risk are the OA, so the private keys we use that are stored in our hardware wallets, so notably using the CDSA. Private payments are using in the UTXO model elliptic curves, the consensus BLS signature, and the availability samplings. So basic, our roadmap at ZKNOX is to solve all but the last point, which means we are not working on proving system, but on these signatures. Okay, so good news. ARCR has made a very good work for us during the 8 previous years. And clearly they have chosen lattices. So we won't argue about that. We could debate and reinvent the wheel here in Web3 because we love to do this. But basically, lattices has won this contest for many reasons. Actually, the problems they are relying on, we have now very good confidence about them, and they provide a very good complexities, both for computations and for the bandwidth. So, for instance, if you look at the size of a signature, so Sphinx is 17,000 bytes, while for Falcon it's 666 and 2K and half for dilithium. So it means you can have Falcon or dilithium on a QR code. If you want to have a Sphinx on a QR code, you will have to use many of them. So it will not be very practical. So Falcon appears as the most suited for our on-chain constraints, but it is known to have to give very hard time for integration at the hardware level for the signers. And also it provides a pleasant feature compared to Dilithium. Falcon has an recover version, which is very similar to how we are using ECDSA signature in Ethereum. We are using EC recover, which allow to recover the public keys that have been used to authentify the transaction. Okay, so in our roadmap, we follow a progressive roadmap. So the first step to be able to deliver the smart contract is performed. I provide the link for our GitHub, so do not hesitate to use it. It is provided as public goods. There is hackathon at the end of the week, so do not hesitate to use it for demonstrating migration transition to the post-quantum era. Next step will be to provide a RIP and merge this into nodes. So we have our forked guess implementation, then to provide an EIP, and in the long term to remove EOAs, because there is also other points of failure. For instance, the bundlers. We forgot about the bundlers. Okay, so the Solidity, it's working. I will talk about the results. It enables cheap experimentation on L2s. So even if it's 2 million gas, okay, you can already use it in production. So step one, the hot wallet, and we will talk a bit later about the hardware implementation. So those are our implementation results. So this is less mind-blowing. Know that Antonio's kind of spoiled our results, but what we had before was 24 million, and some claims that it's impossible to to have a practical result. I don't know if 2 million is still practical. It's still very expensive, but we are kind of very confident that maybe you will gain 10% by trying to optimize your contract. But we are two cryptographers. We have used the best entity, which is the core multiplication of polynomial algorithm, the best algorithm at the state of the art. Everything is yield. So honestly, if you win more than 10% on gas, it will already be high. With the AVM constraints, we are using 256 words. There is no vectorization because lattice computation can be very efficiently vectorized. So there are some old EIPs about vectorization. It could totally benefit of the level of vectorization we have in Solidity. But for now, this 1.8 million is like a limit. Okay, so what we did, so we were very slightly not compliant to the NIST standard, or at least we have a fully NIST compliant standard at 7 million gas. Just replacing the check that is used here by Ketchak, we dropped to 2 millions. And actually, if we, as Antonio said, if we had a whole EIP, when we bench at the node level, the C implementation of Falcon and ECDSA, it's quite close. So the gas code should be the same if ever adopted. And during the past, we managed to find some tweak of Falcon, which is Hyper-V, which enable a recover version without having to make entity inversion. Okay, so small stuff. So those are the results. And to be complete, we also implemented Dilithium, which is the other candidate. Actually, Dilithium for non-on-chain constraints will be the one that will be cheap by vendors, because as I said, for signers, it's very easier to implement Dilithium than Falcon. So Falcon is perfect for verification, but this is kind of the sense of history. Why do we use ZK? It's because we want to have fast verifier, and we let all the burden to those providing the proof or signing. So for I think for Ethereum, vendors should make their homework, because for the chain, Falcon is better. But anyway, if you want to use Dilithium, we provide it out as well, and it's 6.6 million gas. Okay, so to conclude, for the verifier, so Falcon is 4 times cheaper than Dilithium, so that's a good point to adopt it for the IP. It's very straightforward to implement for the node. Just follow NIST recommendation. the EVM-friendly version is preferable for the experimentation. So this tweak of specification using a Ketchak instead of check. And we also proposed an independent EIP, which is entity. So entity is a multiplication of polynomials. And actually, if instead of choosing Falcon or dilithium, we adopted entity, we would be able to implement on top of it very efficiently either Falcon or dilithium. And if we look at EC recover, it's kind of, we have taken it the other way. You can tweak EC recover to do a point multiplication. It's kind of not the way it should be. We should use point multiplication to make the signature. So for, in our perception, it would be better to have entity as building blocks, because even if specification change or if we have some tweak, and we will talk about ZK-friendly tweak that we are working on, entity could be the way to go. So this is something that we have proposed, and it's 7885. It's little name right now. Vectorization would be very efficient to speed up entity. So there are, we have had some collaboration with the EVM Max team, and they managed to have like a very high gains. It's kind of hard to separate the vectorization from the compiler that is very efficient, but at least 80% gain should be expected. So if we had to choose one, EVM Max is more flexible than entity, but it's also more harder to implement in the core. Okay, so now that we have this solidity, we are very happy. We can already secure all our smart accounts with 4337 or 7702. If we imagine that at some point we are able to disable the EOA, which is another EIP that should be adopted, in my opinion. So now, going back to signers. So the main constraint for hardware wallets will be the RAM. Hardware wallets are very limited amount of RAM, so integrating Falcon into it will be a challenge. A challenge we are working on. And one way to solve this is to use oblivious RAM. So oblivious RAM is to extend the RAM of the device by using the host memory, so your laptop or your phone, and using confidentiality and integrity mechanism on the host memory. You can extend the RAM and maybe use this to implement the signer. So this is something we are working on. Recently, Ledger shipped Vanadium, which is a VM. This is another way to go, but I think it will be slower. So this is okay. This is the thing. One of the subjects we are working right now, but we shall ship a signer, hardware signer verification before the end of the quarter. Okay. So conclusion. On-chain constraints, they shall be prioritary. So Ethereum shall lead the decision, not tied to what the vendors will announce, but to the on-chain limitation. And using oblivious RAM or other mechanism, it should be possible to tweak the implementation to be able to have this hardware wallet implementation. Okay, so we are happy. We see that at some point we will manage to have the signer for. I didn't say about it, but for dilithium it will be possible to do it. There are papers by NXP. They are able to implement dilithium in 3 kilobytes. Okay, so now what are the next steps? So the next step is to prove. By proving, I mean to have a ZK proof of Falcon or dilithium, because we at the beginning of the talk we talk about private payments. So it would allow both to integrate this ZK version of Falcon or dilithium into a ZK VM, allow post-quantum private payments, and also maybe be another candidates for the consensus layer batching of signature for the consensus. So there are several teams working on this. There is Labrador. So Labrador, they took it the other way. They tweaked their proof system to be able to prove Falcon. We are working on the other way, tweaking Falcon to make it easier to prove. Okay, so what we need to do. So we need to operate on non-native fields, and this is what is very expensive. So if you have some experience about ZK implementation, working on non-native fields is called emulation, and emulation gives you a factor 100, basically. So switching the field is what you can do. This is why what is done by Railgun or by Bandersnatch or the star curve by Starkware, but it's not as easy to tweak a post-quantum lattice candidate than to generate another elliptic curve. So how to introduce a minimal tweak in the specification to obtain ZK-friendly version is something we're working on. Okay, so first there are some very naive tweak and abuse that you can do. So replace the F function. So it's using. So we have been using Ketchak, but Ketchak is not ZK friendly. So this means that if you want a ZK friendly version, you replace it by Poseidon or maybe Blake. There was a talk by Starkware about ZK Blake implementation this morning. There are also some hints. Hints are some additional input you provide to the prover to make it easier to prove. So with Epervier, we have some spare computation in the verification of Falcon. And another way is to accumulate several steps and perform modular reduction, which is something very expensive because it implies division only once. And there are other tweaks where replacing the fields mean recomputing all the different security trade-offs and the proof, because there are many different problems when implementing lattice. And at the intersection, we have to change size of matrices. And we also discovered that Falcon will be prone to overstretch if we use ZK-friendly feeds. So for the ZK proving, dilithium would be a better candidate. So this is something we are still working on. So just to remember for now, so dilithium is more ZK friendly, and yeah, we are working on this ZK dilithium and ZK Falcon implementation that we should ship also during next semester. It's still in the experimental phase. Private payments. So there are 3 weaknesses: the ECDSA that is used in UTXO. The ciphering for the viewing key, and the proof settlement. So proof settlements, using Stark, you will solve it. The problem is the size of the proof. So there are other candidates now. There is Weir. I think they managed to have 128 kilobytes. So this is still like a 100 increase compared to a GROT 16 proof. So it appears to be very problematic for smart contracts. So PQ will break the authenticity and settlements, but this should be solved later, but not the confidentiality. So first, if you have to change something in a Raygun, for instance, is the viewing key. The viewing key shall not use ECDSA from now, because it's very easy to replace this by a post-quantum algorithm for the viewing key, and to resist to a later decryption. But we shall not wait for this. And if you use private payments, okay, have this in mind. Okay, so to conclude my talk, so there are some quite easy solutions for the EOM migration. The contracts are there. The gas costs you're able to concede will guide you in choosing the EVM friendly or the fully NIST compliant versions. We propose this EIP to reduce the gas cost, and to be noticed, it would also reduce the cost of Stark proof, because Stark proofs, they also need to have some polynomial multiplication at their core in the solidity contract. So this would also benefit to layer 2 using Starks. And we are still working on the hardware signer. And for the consensus layer, okay, our work is still very experimental. We have no idea what will win between, okay, hash-based signatures, the Labrador, but we are providing additional inputs, and I think it would be very interesting to work with the Weir team to see if we manage to plug our ZK-friendly version into Weir to provide something for the consensus layer. And that's it. So remember, all that we provide is open source, public good. We would gladly help to any wallet, dApps to integrate it in the framework. Here is the GitHub link to the repo. So the guest fork, the smart contract implementations. And that concludes my talk. And I think we have a little time for questions.